Swayam Prabha. Digital India. Educated India.
So in the last few classes, we have looked at various principles of hydrostatics and in general fluid statics. In this particular class, we will look at fluids under rigid body motion. So fluids under rigid body motion refers to flows in which the fluid either translates or rotates like a rigid body. We have already seen that in order to have deformation, we need a gradient in the velocity field. And this meant that if we have a fluid element like this, and if you have a higher relative velocity of the top face with respect to the bottom face, it would lead to a deformation of the fluid element. However, if both the velocities are equal, then the fluid body would simply translate without any deformation. So now let us look into the theory of it. We've already seen that the body force acting on the fluid is equal to minus gradient of the pressure, and we have looked at the interpretation of the negative pressure gradient. However, if the fluid is undergoing rigid body motion, this force must be equal to the rate of change of linear momentum of that object. So in general it could be mass times acceleration, but we recall that this force is per unit volume. This force was evaluated on a per unit volume basis, so it will be mass times acceleration of that element per unit volume, and so it would simply boil down to rho times A. So we have rho A is equal to minus grad P. Now let us consider a flow with a constant acceleration. So this would imply rho AX is equal to minus del P del X. I'm just expanding this particular equation. Then we would have rho AY is equal to minus del P del Y, and similarly we will have rho AZ will be equal to minus del P del Z, but there will be another added body force that will be due to gravity minus rho G. So here I have explicitly not written gravity, but in general the force acting on a fluid element is due to the pressure gradient and the action of its body weight, that is gravity. So plus rho G, but when we substitute that G is equal to minus G acting in the EZ direction, we obtain this particular relationship. So these are the three equations which govern. So now let us look at how we can use these equations to solve a very simple problem, that of a sloshing tank. Let us consider a tank as shown in the problem. Now the tank is moving at some acceleration, and there is a level of water in this, and so when the fluid accelerates, we know from experience that the fluid will be pushed towards the back in the frame moving with the vehicle. And there are various examples where you can see this when you are trying to have a cup of coffee or trying to drink water. inside a moving car. When the car moves with a constant velocity, that is when it's not accelerating or decelerating, the level of water remains fixed. However, the moment the car accelerates or decelerates in order to avoid a bump or in order to overtake someone, you will see that the level of water shifts and it becomes difficult for you to drink water. So, because of this acceleration, the liquid would become something like this. So, the question is, what is the equation of this particular free surface of the liquid? So, the way to do it, let us first identify the fact that all the points on the free surface are at ambient pressure. Meaning all over the interface between the water and the, so this is water, this is air. So at all points on the interface, the pressure will be constant. So I can write at any point. So let me call this axis as x and let me call this axis as y. So not y, let us use the convention used before, and that will be z. So dp in this coordinate system can be written as del p del x dx plus del p del z dz, and this statement is true regardless of whatever is going on. Now from the previous equations we know that del p del x is going to be equal to, or rather minus del p del x is rho ax and minus del p del z is equal to minus rho g, and if there is some other acceleration plus rho az. So this follows from the previous equation. Oh, rather minus del p del z equal to rho az plus rho g. So I have made a small sign mistake. That's okay. So now let us substitute these equations over here, and in fact in the given problem we only have ax, az is equal to 0. So this particular expression becomes rho g, and it is given that the value of the acceleration is equal to 0.5 times gravity. So this will be equal to rho times g upon 2. So from these two equations we may write del p del x equal to minus rho g upon 2 and del p del z is equal to minus rho g. Consequently, in this particular equation we can then write dp as minus rho g upon 2 dx plus minus rho g times dz. Now recognizing that all over the interface the pressure is going to be a constant, when I write this equation at the interface, so for any point on the interface we have dp is equal to 0, because over the interface, I reiterate, over the interface the pressure is ambient pressure and it does not change with x and y on the interface. So these are all the points on the interface. So the choice of x and y are such that the x and y constrain the point to be on the interface, not anywhere else randomly. Okay, they will constrain it to be on the interface. So at the interface dp is equal to 0. So we have 0 is equal to rho g upon 2 dx plus rho g dz. This implies at the interface dz upon dx is going to be equal to, so we've taken this on the left hand side, so minus rho g upon 2, and that thing will be divided by g rho g. So this becomes minus half. So thus if we integrate this equation we have dz dx equal to minus half, right, and this implies that z is equal to minus x upon 2 plus constant. So it's like an this is an equation for a line with a negative half slope with a certain intercept. And the way to find the intercept is that given this shape exists, given the dimensions of the vehicle, I can find out the volume of water in the deformed condition in terms of the offset, and I know how much volume already existed in the vehicle or in the tank mounted on the vehicle in the initial time. Because there is no water sloshing out as such, we can equate these two volumes and evaluate the value of the constant. It is as simple as that. Let us consider a problem in which we have a rectangular tank whose length is 10 meter and the height of the tank is 2 meter. It is given that initially the tank is filled with water to a height of 1 meter. The tank suddenly accelerates in the x direction with an acceleration equal to that of gravity. So the question is, will water spill out? So will water spill out? So we know that when this container will accelerate towards this direction, the water will have a tendency to form a surface like this. So accordingly, we have to find out whether or not there will be any spillage. So we have rho times AX equal to minus del P del X, and rho times AZ is equal to minus del P del Z minus rho times G. And we also know that dP, which is equal to del P del X dx plus del P del Y dy. And at the interface, dP equal to 0, because at all the points on the interface, the pressure is equal to the ambient pressure, and therefore at the interface also, okay, this will not be dp dy, but rather it will be dp dz. There is no acceleration component in the y direction. So 0 equal to del p del x dx plus del p del z dz, and this implies that for the interface Ez dx will be equal to minus del p del x upon del p del z. Now substituting these values over here, we obtain dz dx at the interface is equal to minus rho times ax divided by, so del p del z. We know that there is no acceleration of the container in the y direction and the z direction, and thus this term will be 0. The only body force acting on the mass of fluid is uh, in the downwards direction, that is towards gravity. So del p del z is equal to minus rho times g. In fact, minus sign is there, so del p del x is rho. So this particular term in the bracket is equal to minus del p del x. Rather, it is equal to del p del x, and we have a minus sign over here. So this becomes minus ax upon g and because AX has a magnitude of 1, this particular term becomes equal to 1. So with this, we have dz dx for the interface equal to minus 1, and thus z equal to minus x plus c. Now, if uh, so, let us take a step back. So dz dx is sort of this particular angle, the angle made by the fluid interface with the x-axis. So dz dx is like tan of theta. I mean, since we're taking it along the negative direction, so ideally it should be taken with the positive x direction. If we take it with the negative x direction, this sort of becomes our x direction. Don't be confused with the actual x and z coordinate system. This is simply writing down the magnitude of tan theta. So tan theta is the angle of the interface, and it will be equal to 1 as per our calculation. But if we keep the general acceleration term, this will be equal to ax upon g. So it will not be equal to 1, but it will be equal to ax upon g. Now, in case there is spillage, the interface, so what will be the angle that the interface makes? So when spillage occurs, the tan theta will be equal to 2 meters length divided by 2 meters height divided by the length of the tank. So for spillage, tan theta spillage will be equal to 2 upon 10. This is equal to 0.2. This is equal to ax upon g. So this particular term implies that when ax equal to 0.2 times the gravity, that is the acceleration in the x direction, is 0.2 times gravity, then the interface will become something like it will just be touching the edge of the beaker. Any acceleration which is larger than 0.2 g will result in spilling out of water. So in this case, yes, water will spill out. As a matter of fact, the problem that we just considered, it had a rectangular tank, and it almost made us feel like, yes, there will be a deformation in the interface and fluid will spill out. But this entire analysis is equally valid for the case of objects of any size. So we can take a cup. So if the cup is filled with water like this, right? When we suddenly accelerate this beaker or cup of water in the x direction, so the interface will again climb. So the slope of this particular surface, so if I have the side view of this surface will have the same motion despite it being a non-rectangular cross-section area. So this angle will be the same as this, because hydrostatics, it does not really depend on the area of contact at this point. Okay, so you can have two beakers, one like this and one like this. The pressure, if the level of water is the same in both the beakers, the pressure at this point will be equal. And because it does not depend on the volume, it's simply rho gh. So it does not depend whether the shape is a cylindrical or any arbitrary cross section, the interface is governed by fluid statics and it will make the same angle. Let us consider another problem in which we have an inclined plane and say the angle of the plane is alpha. So the question is, if we have a tank on wheels rolling down the plane, what is the angle of the water? So what angle does the water make with respect to the vertical axis? Let's call it theta. So effectively this angle is theta. So let us assume that the wheels are frictionless, meaning it is rolling freely down the inclined plane. So in that case, so first of all, gravity acts on the mass of body in this direction, and this is the direction of the acceleration of the entire object. So if the wheels are frictionless, whatever force acts on the body along the plane will be equal to the mass times acceleration of the object. So we can say F along plane will be equal to mass times the acceleration along the plane. So A plane is equal to force along the plane divided by the mass, and the force along the plane will be equal to the weight, which is mg, but the component of mg along the plane, which will be, so if this angle is alpha, this angle will be alpha, and corresponding this angle is 90 minus alpha. So cos of 90 minus alpha is going to be sin alpha. So it will be mg times sin alpha, this divided by m. So m cancels out. So acceleration of the entire object in this direction, which is the direction of the plane, so AP, let's call it, will be equal to g sine alpha. So now this g sine alpha is along the plane, that is to say this is the angle alpha. So if this angle is alpha, that is this angle is alpha, this angle will also be alpha. So this AP, so in the x direction the component will be AP cos alpha, and in the z direction the component will be AP sin alpha. Moreover, gravity also acts in the z direction, so we will have plus g. So we have minus del p del x equal to rho ax and minus del p del z minus rho g is equal to rho az, where we've written out schematically what the different accelerations should be. So from this diagram, ax is ap cos alpha and az is ap sin alpha, but look, the direction is in the minus z direction, so az we must substitute as minus ap sin alpha. So this is minus rho ap sin alpha. So minus del p del z is equal to rho g times rho g minus rho ap sin alpha, and from this equation we have del p del x equal to minus rho, so ax is ap cos alpha. So along the interface we have dp equal to 0, but dp can be written as del p del x dx plus del p del y dy dz. I keep writing it as y, but it's actually the z direction. So dz dx is equal to minus of del p del x upon del p del z, and this is equal to minus of, so del p del x is rho ap cos alpha divided by del p del z, so minus sign goes over here, so rho ap sin alpha, so del p del x was minus rho ap cos alpha, so there has to be a minus sign over here, and del p del z is equal to rho ap sin alpha minus rho g. So rho cancels from all sides, from all the terms, and this minus minus becomes plus, so it is equal to ap cos alpha upon ap sin alpha minus g, and noting that ap is equal to g sin alpha, we can write this as g sin alpha cos alpha divided by g sin square alpha minus g. So essentially it becomes equal to sin alpha cos alpha divided by sin square alpha minus 1, and we can equivalently write this as, so dz dx is essentially, so we multiply by 2 and divide by 2, so 2 sin alpha cos alpha becomes sin 2 alpha, and twice sin twice sin square alpha minus 1, so this is going to be minus cos square alpha, so divided by minus 2 cos square alpha. So essentially the slope is going to be sin 2 alpha divided by 2 cos square alpha. Let us do the calculation when alpha is equal to 30 degree. So when alpha equal to 30 degree, we have minus sin 60. So minus sin of 60 degree divided by 2 cos square alpha, so cos square 30. So sin 60 is root 3 upon 2, and we have a half from this term, and cos square 30 is going to be square root of 3 upon 2 whole square, so this is going to be 3 upon 4. So this terms cancel and it becomes minus 1 upon square root of 3. So effectively the angle that we want is already aligned with the negative direction, and it's easy to figure out. So tan of the theta that we have mentioned in the diagram is actually going to be minus of del dz dx, because this slope is as if x is reversed. Okay, the slope that we have written dx dz dz dx is actually in this coordinate system. So when you flip x, this particular tan theta, uh, so in the normal coordinate system this would have been our theta, but when you flip x, this becomes the theta, which is what exactly we want, and thus tan theta is equal to minus dz dx, and this is thus equal to 1 upon square root of 3, and this particular angle therefore corresponds. So for theta is equal to 30 degree, we have tan theta equal to 1 upon square root of 3. Essentially, it means that the angle of the incline, which is 30 degree, because we did the calculation for an incline of 30 degree. So the angle of the incline and the angle that the interface makes with the horizontal, they are identical. But is it always going to be the case? And while we did obtain an expression numerically, it is far more easy to see that this result is actually more general, because if we take a step back, this is essentially, or we can just start modifying from this step. So this is sine 2 alpha by 2 cos square alpha. So in the coordinate system where x points in the opposite direction and z is over here and this is theta, so we have dz upon dx equal to tan theta, and this is sine 2 alpha upon 2 cos square alpha. Yeah, and this is as good as writing 2 sine alpha cos alpha upon 2 cos square alpha, and this is equal to simply tan alpha. So theta is equal to alpha. This means that when a tank full of water is rolling down an inclined plane, the level of the water is aligned with the angle of the incline. So the level of water with the horizontal, this angle and this angle are identical. This is quite a counterintuitive result if you ask me, but I want you to think about it deeply and try to make a justification why this is the result that you obtain. So let us proceed with finding out. So this was one kind of motion where it was a rectilinear motion. We can have another kind of motion where we can take a beaker containing a liquid and then we spin the beaker on a turntable. And as a child, you might have done something like this. I mean, even as an adult, you could have tried something like this, no problem. So initially, if there is no rotation, the fluid remains flat. Upon rotation, you will observe that the fluid gets thrown to the side and there is a kind of parabola or rather paraboloid that starts forming in the fluid. Notably, the entire fluid rotates with the same velocity as the velocity of the turntable, but it is not instantaneously the case. When the turntable starts rotating, the effect of viscosity begins to propagate into the fluid, and after a while, the entire fluid begins to rotate with the same velocity. However, these discussions will be more understood when we consider what viscosity and viscous propagation is. For now, it is sufficient to know that this kind of rotation makes the body move with a constant velocity. So let us assume that the entire beaker is rotating with a rotational velocity omega. Our task is to find out the equation of this particular shape. And it is important for us to acknowledge that this problem is an axisymmetric problem, meaning if I draw a 2D diagram of this, and if this is the interface shape, I can choose a coordinate system, something like this. This can be R and this can be Z. And the theta angle does not appear in our problem. So now we have to rewrite the equations of motion in the RZ coordinate system. So once again, for any point we can write dp as, now it will be del p del r dr plus del p del z dz. So this is the dp in a cylindrical polar coordinate system. Now we can write in a straightforward manner that del rho times az is going to be minus del p del z minus rho times g, and this is true. However, there is no acceleration of the beaker in the z direction. The only force acting on the fluid elements in the z direction will be that due to gravity. Thus this particular term will vanish. So we have del p del z is equal to minus rho g. Similarly, because of the rotation of the beaker, a fluid element at a given distance r will experience a centripetal acceleration as seen from the lab coordinate system, and the magnitude of that acceleration will be omega square r, and the direction will be opposite to the radial direction. So the radial direction is always pointing away from the beaker. So instead of that, it will be pointing inwards. So rho times ax, or rather not, it will not be ax, it will be ar, is actually minus rho omega square r. This is the acceleration on a fluid element in a in this rotating beaker. So we have this equal to minus del p del r. Okay. So fundamentally these two are equal and these two are equal. That is how we have arrived at this particular expression. So thus we have del p del r is equal to rho omega square r. So with the help of these two expressions, we can now substitute them in the expression for dp. So we have dp, and again at the given interface dp will be 0. At the interface dp will be 0, meaning the choice of r and z on the interface will be such that we always lie on the interface. R and z cannot be arbitrarily chosen. Okay. So dp equal to 0 at the interface. This implies this equal to del p del r times dr. So rho omega square r dr plus del p del z dz. So del p del z is minus rho g dz. So when this is equal to 0, we have rho omega square r dr is equal to rho g dz, and essentially we have dz upon dr, or I mean we can simply integrate it at this point itself. So essentially we have rho omega square r square upon 2 is equal to rho g z plus a constant of integration. Okay. Now one easy way of finding out the constant of integration is attaching the coordinate system at the minimal point of the parabola. So obviously this equation describes a parabola where c is simply an additive offset in the z coordinate. C is just an additive constant in the Z coordinate. So I can very well choose the coordinate system to be something like this, so that Z equal to 0 corresponds to the bottom point, and essentially Z equal to 0 corresponds to P is equal to P atmosphere. So essentially I can simply make the constant to be 0, and I will have rho omega square r square upon 2 is equal to rho gz, and this is the equation of the interface. I can cancel out rho, no problem. So essentially at z equal to 0 we have r equal to 0 and p equal to p atmosphere. For all the other points we can find out the pressure. How can I find out the pressure at some other point? Well, we can simply write down the expression for dp and integrate it over these 2 points. Essentially dp is rho omega square r dr minus rho g dz, and p is thus rho omega square r square by 2 minus rho gz plus constant, and the constant that we have chosen is such that in this particular coordinate system r equal to 0, z equal to 0 correspond to p equal to p atm. So the constant when r equal to 0, z equal to 0 becomes p atmosphere. Therefore we have p minus p atmosphere is equal to rho omega square r square by 2 minus rho g z. And with the help of this particular equation, you can put in any r and z you want, and that will evaluate the pressure at that given point. Okay, so this is how you do it. But remember, at all the points on the interface, P you will find out that it is exactly equal to P atmosphere, because these are all the points on the interface. All the points on the interface are parameterized by a combination of R and Z which satisfy this particular equation. So if this particular equation satisfies the equation of the interface, you can substitute exactly this expression over here, and the right hand side will become 0, implying P equal to P atmosphere on the interface. So both these equations are consistent, but this equation can help you find out the pressure at this point or at this point or at this point, any point. Okay guys, any doubt so far?
Sir, just a basic doubt.
Yeah.
Can you explain why at the interface we will be in case of rotating?
Can you repeat the question? I could not get.
But can you just explain why the dp would be 0 at interface in this case?
So dp is by its very definition. Okay, so the interface between any two fluids. So if this is air, rather this is water, this is air. Given that this interface exists, there must be some forces acting on the interface which have caused the interface to become like this. But atmospheric pressure acts equally at all points, meaning, okay, first of all, let us assume that these differences in altitudes are not humongous. They can be at best 1 meter, 2 meter, doesn't matter. So the added pressure on top of the atmospheric pressure because of a column of air that is 1 meter high will be negligible. So the pressure contribution rho air GH as compared to P atmosphere. Let us look at this. So what is rho air? 1.3 kg per meter cube. What is density? It is so the gravity is 10 and say height is 1 meter. So this becomes a pressure of 13 Pascal, whereas P atmosphere is 101,325 Pascal. So it is just a very small fraction of the atmospheric pressure. So you can very well assume that all the points on the free interface are at the atmospheric pressure. In fact, even if you take a column of air of 100 meters, right, hardly anything changes. That is why you can assume that assumption to be true. So all the points on the interface are at the atmospheric pressure. Well, They are approximately equal to the atmospheric pressure, and hence at any 2 points on the interface, if I move along the interface, dP has to be equal to 0. Let us consider a problem in which we have a U-tube manometer as shown, but it is now rotating, or rather it is held rigid with respect to this particular axis, and this particular axis rotates at a certain RPM. So let's say that this entire object rotates about this axis at an RPM of 6. So the rotation rate is 6 RPM. And suppose we know that the distance of the center of the manometer is approximately 5.8 meter. It is given that the gap between the limbs of the manometer is 7 centimeter. We want to determine, so naturally because of the rotation, there will be fluid which will go up in this particular limb as compared to the left limb. So we want to know what is the change in this particular height. Let's call it h. So this is what we have to determine. Now look, right away we can see that the gap between the two limbs is only 7 centimeter, while the radius or the mean location of the manometer with respect to the axis is 5.8 meter. So it is 7 times 10 to the power minus 2 upon 5.8. This is a very small number. It is approximately 1.2 10 to the power minus 2. So the limb, when seen from this point, will appear to be a single object which is kept at a distance of 5.8 meter, because this gap is much smaller than the radius. So what is the angle if we make this particular calculation? So because of the fact that this is held fixed with respect to this axis and it is rotated, the centrifugal acceleration will be equal to omega square r average, and omega is 6 rpm, so 6 times 2 pi upon 60, so this is in radian per second square times 5.8, and this comes out to be 2.289 meter per second square. So on this mass of fluid, this is the acceleration. So let us say this is ax. Now in the z direction, the acceleration is going to be g, which is 9.81 meter per second square. In that case, we can again say, because these two sort of the free surfaces, dp at that free surface is 0, which means del p del x dx plus del p del y, again del p del z dz. This implies dz upon dx is equal to minus of del p del x upon del p del z. and this is equal to minus of rho ax divided by rho az, or rather rho g. So essentially it means that the slope that we want to find will be equal to the ratio of, so tan theta, if I call this theta, will be equal to the ratio of the acceleration to gravity. It is very easy to find this out. So tan theta in this case will be 2.289 divided by 9.81, and this tan theta will be equal to the height of the column divided by the gap, which is 7 centimeter. So this implies the height will be equal to 2.289 divided by 9.81 times 7, which is 1.63 centimeter. Okay, so in case you are wondering about that step jump, so in the coordinate system in which we view the object, the acceleration, if this is the ex direction, the acceleration will be in the minus x direction. So we can write rho ax equal to minus del p del x, but ax will be minus omega square r. So minus rho omega square r, because it will be in the lab frame, it will be the centripetal acceleration, and rho az equal to minus del p del z minus rho g. Az will be 0, which implies del p del z will be equal to minus rho g, and this particular statement implies del p del x is equal to rho omega square r. So combining this, so rho gets cancelled, so this is minus of ax upon g. I mean, let me not skip this step. So this is equal to minus of, so del p del x is rho omega square r divided by del p del z is minus rho g. So this minus sign cancels, so it becomes omega square r upon g. And this is exactly as this statement. So that is how you find it. But we found out the height, that is okay. But we have made the assumption that the entire object has sort of a mean acceleration. So this result is found out to mean acceleration. But the acceleration at this point of the fluid and the acceleration at this point of the fluid is different, because this point of the fluid will have an acceleration smaller than the acceleration at this point. And this entire thing is tantamount to some large mass of fluid which is rotating and causing the shape of the fluid to become something like this. So essentially, this assumption is like a rectilinear motion. So this assumption says that the surface of the air water interface will be straight line. That is, if we had a beaker and we accelerated, in this case the acceleration is in the opposite direction, the centripetal acceleration, the surface is something like this. So in the first result, when there is a mean acceleration, this is assumed to be a straight line. But we know that there is some rotation about some axis, and Yes, the assumption is this distance from the mean location is quite large compared to the distance of the limbs. But regardless, the actual surface would be a paraboloid. The actual surface would be a paraboloid. And because it is going to be a paraboloid, the equation of this free surface, as we have already found out just before this section, is going to be c plus omega square r square upon 2g, where r is measured from the axis of rotation and this is z. In this case, omega is 6 rpm, so essentially it is 6 into 2 pi upon 60 radian per second, and we want to find out z2 minus z1, basically something like this. So from this point of the parabola, this height is suppose z1 and this height is z2, then the difference in the fluid level will be equal to z2 minus z1, and it is simply going to be omega square upon 2g times r2 square minus r1 square, and this will be equal to omega square upon 2g times r2 plus r1 times r2 minus r1, and this is going to be omega square upon 2g. Let me divide by 2, so this is r2 plus r1 upon 2, and let me multiply by 2 times the distance in the radius. The distance in the radius is 7 centimeter. This will be 7 times 10 to the power, in fact, yeah, let us do it like this. So it's 10 to the power minus 2. Okay, so and this is the mean distance, so which is going to be 5.8. So this is essentially, so this is pi by 5 radian per second. So this is pi upon 5 square upon 2 times 9.81 times 2 times 5.8 times 7 times 10 to the power minus 2 meter. And let me crunch this into my calculator. So pi by 5 squared divided by 2 into 9.81 times 2 times 5.8 times 7e minus 2. So this comes out to be 0.01633 meter. Essentially, this answer is also 1.63 centimeter. This is the same as what we had obtained earlier as well. And essentially, what the meaning of it is, the paraboloid curve, it is on a radius that is so large that over a small distance of 7 centimeter and at a distance of 5.8 meter from the axis, the shape of the paraboloid and the straight line joining the 2 points is approximately same, and hence the solution obtained from both these approaches is the same. The shape of the free surface does not depend on the object shape. It can be a manometer, it can be a cup of water. All that matters is the acceleration that is subjected to, and that will dictate the shape of the free surface. With the help of that, we've been able to analyze many problems. With the help of that, we've been able to see how free surfaces form, and lastly, we've seen how the two approximations, that of a paraboloid and that of a straight line, give us a very similar answer for large radius of rotations.